Hello everyone, this is Dennis and you're on the Electro channel. Today we'll be talking about bistable load switching modules. These modules can remain indefinitely in two modes of your choosing, either on or off. The module works very simply. The first press of the button turns it on, and the second press turns it off. These modules can be called electronic latching buttons. They allow you to turn any device on or off with just one press of a button. I bought the modules on AliExpress. There are two types. I'll tell you the differences now. Both modules are almost identical. Power is supplied from the left, and the load is connected to the right. Here I've shown a light bulb and a motor. But in reality, you can connect absolutely any load, anything that comes to mind. The first low voltage module operates from 3.5 to 5.4 volts. The second module is a higher voltage module. Its supply voltage range is much wider, from 4.5 to 26. When turned off, in standby mode, the first module draws very little current, just 300 nanoamps. The second module draws 4 times that amount, at 1.3 microamps. The stated load current for these modules is quite impressive, up to 10 amps. Whether this is true or not, I'll demonstrate during testing. The low voltage module has few components: a button, capacitors, a 75 amp field effect transistor, and a small 6-pin microcircuit just below. This is what controls the entire module. The circuit is quite simple. When the button is pressed, the microcircuit output opens and current flows to the transistor gate. The transistor opens, and through it, the load is powered by the power source. The high voltage module has more components. It has the same control microcircuit and transistor. In addition, there is a 12-volt Zener diode, a 3.6-volt voltage regulator, a dual-signal inverter, and a bipolar transistor. The reverse side of the boards is bare except for the tracks. The negative terminal in both cases runs directly across the entire board. The circuit is connected via the positive terminal. The modules are very small. The photo shows a comparison with a matchbox. Thanks to their compact size, they can be integrated into almost any device. If the small button located on the board is inconvenient to use, you can run wires from it and connect your own button. The button should be normally open. The length of the wires doesn't matter. To test the module, I built a small circuit. I powered them from this converter. This multimeter will show the current consumed by the modules, and this one will show the output voltage. At first, I wanted to see if the modules really consumed nano and microamps when off. But it turned out that my multimeters simply couldn't measure such a microscopic current. I was only able to measure the current when on. This low voltage module draws 1 milliamp. It consumes this current for its operation. No load at the output. After pressing the power button, the output voltage slowly begins to drop. This only happens when there is no load. Apparently, the capacitor is discharging. Then I wanted to see if the module's current consumption would remain the same when it is powered off if a load was connected. To do this, I took a resistor and connected it to the output. The input current did not increase. This means that the circuit is completely turned off and the transistor is reliably turned off. Even when powered off, no current flows to the load. I turn the module back on and disconnect its power supply. The output voltage naturally disappears. Then I reconnect the alligator clip to the wire. The output voltage doesn't appear until I press the button again. This means the module doesn't remember its last state. If you disconnect and reconnect its power, the module will always be off. The second module, the high voltage one, is the same. Only when turned on does it consume 4 milliamps, not just 1. I first measured the current with a 5-volt supply, then increased the voltage to 12. The current increased by only half a milliamp. Now I'll try running a higher current through this module and see how it heats up. I'll start with 9 volts. I'll load it with an electronic load. The current is over 5 amps and the voltage has dropped slightly. The voltage drop occurred not on the module, but on the power supply. I'll connect a multimeter to confirm this. The input voltage is 8.53, and the output is 8.49. The difference is only 4 millivolts. The board has already warmed up, but not much. The temperature feels about 40 degrees Celsius. I'll increase the voltage to 12 volts. I press the button on the module. It turns off and on again. The board is still warm. It's not overheating. I'll increase the voltage a little more. Everything works fine with these current and voltage values. Unfortunately, due to issues with my equipment, I can't immediately verify the module's stated specifications in this test. Therefore, I'll test the maximum current and maximum voltage separately. I'll lower the voltage to 12 volts, and now I can increase the current. I'll increase the current to almost 8 amps. The board has already gotten really hot, but it's still working perfectly. I'll increase the current even more to 9.5 amps. The board still works and hasn't burned out. Although I didn't load the board to the manufacturer's stated 10 amps, I think it can handle not only that, but even more. Of course, not continuously, but not for long. The board has already gotten very hot and is starting to burn my fingers. It got very hot very quickly. If it's running for long periods at that current, it will definitely need a heatsink. Now I'll turn the current down and increase the voltage. Currently, the board input is 22 volts. At 1 amp, the voltage on my power supply drops to 20.5 V. The board can easily handle such a small current and is already starting to cool. To control a very powerful load with this module, one that consumes more than 10 amp, the module's output can be loaded with a transistor or relay. In the diagram, I showed a simple example using a field effect transistor. In place of the light bulb, you can use any load that consumes tens of amp. In this case, the entire enormous current will flow through the transistor. In reality, this circuit would look like this. The load is 2 halogen lamps. As I mentioned earlier, their current will flow through the field effect transistor. In this example, the lamps consume only 6 amp, but a more powerful load could be connected instead. Keep in mind that the transistor will become very hot due to the high current. Therefore, it will need to be placed on a radiator. If you liked these modules, You can purchase them by following the link in the description.